Yes, obviously, first of all, thanks to the organizers for giving me the opportunity to speak here and for hosting this conference. I'm traditionally to use Lyre's nomenclature in the business of cat killing. So I don't really have a problem with this label because I don't particularly like cats. But for those of you who do like cats, it's maybe worth pointing out that we are to equal parts cat rescuers, right? So I think that looks much better on the grant proposal. But so today I don't want to talk about gravitational collapse of the wave function, but about some other issues relating to the question what happens if we couple quantum systems, by that I mean laboratory quantum systems, to gravity. And for that I want to look again at a thought experiment that was proposed a couple of years ago and discussed. I will try to give a slightly new perspective on that with some conclusion, which isn't the conclusion I originally had in mind when I started this talk. It occurred to me during the talk that I was probably wrong about something, but I still think it's interesting to look at. So, to start, first of all, let me notice that the question of quantum gravity, even though it's often presented as such, isn't really just a question of what happens at the Planck scale, right? But it's already the question what happens if we have a superposition of a massive particle. So think of the double slit experiment or the Stern-Gerlach experiment. Doesn't really matter. You have a macroscopic superposition of a mass. It doesn't even have to be a large mass. You need to have some test particle that is sensitive enough to, in principle, feel the gravitational field of that test mass. And you would ask yourself, okay, what happens to this test particle? What is the force felt by this test particle? And you could, of course, look at this in analogy to electromagnetism, because we know that in the non-relativistic regime, gravity is very similar to electromagnetism in a lot of its properties. Where the answer is obvious, right? You would have like the superposition of your source particle would also result in the superposition of the gravitational field, which again then means that you get an entanglement of the state of this field with the state of your test mass. So effectively, you will end up having entanglement of source and test mass. But I think it's important to point out that gravity isn't completely analogous to electrodynamics, and one obvious way to see this is that we still have no renormalizable quantum field theory for general relativity. Right? So there is obviously something that must be different about general relativity. So I wouldn't jump to the conclusion too fast that this analogy should still work in this context. And also, one important way to look at this, more from the perspective of a general relativistic point of view, is that in general relativity, gravity is not a force. General relativity is the idea to unify unify gravity with the inertial structure, and there is mathematically a very crucial difference between forces and the gravitational inertial structure, which is that it gives us an affine space rather than a vector space. So there is no state that is free of gravity, so free of inertial gravity, unless we basically break this unification of gravity and inertia again by introducing some background space-time. So this is the one point of view from the perspective of, okay, how does quantum matter source the gravitational field? A slightly more conservative question to ask is, if I have some given external curved spacetime, how does quantum matter fall in this curved spacetime? And there we sort of have a theory, right? Quantum field theory in curved spacetime is, up to some mathematically, some important mathematical details, right, is in principle a theory that is understood in some sense. But first of all, it's not understood in the sense that we could actually say, okay, how do I describe, for example, the situation of an atom falling in a gravitational field. And the second point is that, well, is it really necessary to use this heavy machinery of quantum field theory in curved space-time if what I want to describe is basically just small corrections of some laboratory quantum system, like an atom or a molecule, due to some general relativistic effects, say time dilation, a mass defect, those are things that have been discussed. And another question that's related to this is the question, how do we formulate the equivalence principle if we are dealing with quantum matter rather than classical test particles. So then again I want to point to the question, or to point to looking at differences between quantum theory and, differences between gravity and electromagnetism. And one of the things that has been discussed in the literature is the fact that matter couples to gravity with its entire energy momentum. So, if we and then we know in quantum theory that we have the Hamiltonian and momentum as operators. So how do we translate that into a coupling of non-relativistic quantum matter to a gravitational field? If you want to go like beyond the Newtonian limit in some sense of having small corrections beyond the Newtonian limit. And so again, the point I'm trying to make is that in order to find interesting effects, it might be more promising to actually look at those regimes where we somehow know that there are differences between classical general relativity and classical electromagnetism, rather than looking at those regimes where the theories are basically have a very analog explanation to each other. So that was just the introduction, and with that I want to have a look at this thought experiment I want to discuss. But before I come to the actual experiment, I try to give a bit of an idea of what I think are basically the ingredients we need. For this, and so all of those are heuristical ideas about how gravity couples to quantum matter, right? Which is important to stress. So nothing of that I claim to be somehow proven truth, right? But all those ideas make a lot of sense somehow from the way we know standard quantum physics works. The first thing is the idea that gravity, which I already said in my first slide, that gravity results in an entanglement between the source and the test mass. So this is related to the proposals, these recent proposals to test whether gravity is quantized. Like I would refer you to yesterday's talk by Masundar, where the idea is if we can manage to create entanglement between two quantum particles through the gravitational field, that would give us some evidence of quantumness there. But again, so this is first of all, this is something that comes out of the analogy to electromagnetism in some sense. So I could do the same experiment with charged particles and the electromagnetic field, and I would get the same predictions. And you have to be a bit cautious about what the conclusions are of this experiment. So if you have as an alternative a mean field semi-classical gravity, which I've worked in a lot, then the answer is obvious. So there is no prediction of entanglement in this model. And so if you want to distinguish between those two theories, Schrödinger-Newton equation, or perturbatively quantized gravity, right, then of course finding entanglement is one way to look at this. But if you make the somewhat stronger claim that by finding entanglement you have an ultimate proof of quantumness of your theory, then you need to be a lot more precise what you're actually talking about. So I would refer you to talk of my student Mal Döner, who will talk this afternoon about some proposals we have recently written down that presents a toy model where you do actually get entanglement for a theory that we think should be understood as a semi-classical theory, where we still have a classical space-time. So that's the first point. So proposition 1, gravity gives us entanglement between source and test masses. The second ingredient is actually not much about gravity, but more our general understanding of quantum theory, which is complementarity. So we know the way we understand gravity, that if we have any way to get which path information for an entangled state, for one part of an entangled state, so in this case for our test mass, that we get an instantaneous loss of interferometric visibility for the other part of the entangled state. Or another way to look at this is the instantaneous state reduction if we have an entangled state and we measure one part of that state. So for that, so first of all, if you think of quantum states in a realistic sense, then what you have there is an obvious violation of Poincare invariance. So you cannot have an instantaneous state reduction in every frame in a Poincare invariant, in any sense of the word. Of course, you can have all types of interpretations where this is not an issue. And one thing I should point out with respect to the thought experiment I want to explain later is that retardation effects are not a problem in this case. So if you think of the electromagnetic gravitational field basically creating the entanglement between your mass, you can always set up a situation where you create a superposition a long time ago, and you already have the entanglement established, and then you do your measurement and have the instantaneous collapse. So you don't have to think about whether, like, the gravitational field propagates with finite time between the two parts of your system. And working, should I just push the keys here? Okay, thank you. And then the third ingredient is the idea that whenever we have a possibility to signal using quantum measurements, that is some violation of causality, which should be avoided. And that is even if the theory we use to describe our quantum system is actually Galilei covariant quantum mechanics. So for that you have to keep in mind that, of course, Galilei invariant theories generally do permit faster than light signaling without problems, right? I can send a Galilei invariant classical particle at any speed I want, also faster than the speed of light. But the idea behind this claim is that the cause of the signaling is not so much in the actual evolution, the Schrödinger evolution of the state, which can just be replaced by some Poincare invariant field equation, the Klein-Gordon equation, but the cause for the signaling is actually the non-local wave function collapse. And so this, of course, also makes a lot of sense, but one should keep in mind that if you want to understand the collapse in some dynamical sense or objective sense, we do not have a Poincare invariant deterministic theory for collapse, right? We don't know if something like that can exist or not. On the other hand, there are ideas, for example, Kant's causal quantum theory that in some situations avoid these problems of faster than light signaling. And the third thing I want to point out is that just because we have faster than light signaling doesn't necessarily imply that we have a violation of causality, right? If in a special relativistic theory you want to violate causality, what you need is basically come up with an experiment where you signal in two ways. So you need Alice signal to Bob instantaneously in her frame, and then Bob signaling back instantaneously in his frame, for example. So in principle, you're not done at the point where you have faster than light signaling. You also kind of would need to still construct this type of two-way measurement situation and consistently describe it to find an actual causality violation. Nonetheless, the argument that faster than light signaling causes a problem is broadly accepted. It is basically the key motivation for collapse models using the Lindblad equation as a way to get the collapse of the wave function. It is also a common argument against fundamentally nonlinear Schrödinger equations in general. So the argument by Chassin, I'm not sure if he's still in the audience, from 89, and slightly older, specifically about semi-classical gravity, the argument by Eppley. So this is where we start. So we say we don't want signaling. We assume complementarity, and we assume that we get entanglement through gravity. And so then the experiment that was originally proposed by Murray and others in 2016 is that we simply, so Alice has in her laboratory has a superposition state, and Bob just sits in his laboratory with a test particle, and Bob now makes the decision to either release his test particle at some predetermined time or not. And basically, if he releases his test particle, the trajectory of his test particle will tell us in which of the two possible states Alice's state is by looking at either the gravitational or the electromagnetic field. And if you do this experiment fast enough, so you have some finite time tau that Bob needs to detect his position, you have some finite time capital T that Alice needs to do her interferometry experiment to find out whether or not she has lost visibility, interferometric visibility in her experiment. If you manage to do this in a total time that is shorter than the distance between Alice and Bob, you obviously can use this as a protocol for signaling. And so this has been analyzed by Belenkia and others who explain why or how the field character of both the electromagnetic field or the gravitational field actually solves this paradox and avoids faster light signaling. So the one ingredient is, if you look at Alice's side, in order for Alice to not already lose visibility by sending out gravitational waves, Alice must basically do her experiment sufficiently slow. So the requirement is that t squared must be larger than the effective quadrupole moment of Alice's superposition state. So you can, like Belenkia and others do this, explain this as a quantum gravity effect by saying, well, we have to require that Alice, by bringing her trajectories together again, does not emit even a single graviton that would send off rich path information. But I want to stress that it's not actually necessary to quantize the gravitational field for that, as long as you assume that gravitational waves carry rich path information. It is enough to also talk in terms of classical gravitational waves being emitted by this process, and then you get the same constant by just requiring the time energy uncertainty relation on this classical process. The other side, so the Bob side, if you look at the original experiment where you just have a classical test mass, right? Then the requirement you have is that this test mass must at least move by 1 Planck length. Okay. Yes, and again, so this requirement of the particle moving at least a Planck mass, you can understand in terms of quantum gravity, where you would then attribute it to the fact that you need to overcome the quantum fluctuations, the vacuum fluctuations in space-time curvature with your position resolution. But again, you can also understand this purely classically, as long as so you scatter a quantum particle, but you have classical gravity, and if you scatter a particle that has some energy and some wavelength, you on the one hand have a resolution limited to that wavelength, but you also must require that the resolution must be above the Schwarzschild radius of your probe particle. And if you put those two together, you again end up with the same requirement that you need at least a Planck length separation in order to be able to detect it. And in any case, so if you use those two constraints and put them together, so using the Newtonian equations to derive what delta x actually is after a given time, and now you put in, then you find that the requirement, those requirements give you that the two time parameters multiplied must be larger than the distance squared between the two, and so this is in conflict to the faster than light requirement that both those times should be shorter than that distance. So you cannot signal faster than light under these circumstances. So an obvious question to ask now is, well, maybe so we've used a classical test particle now, classical test mass, to detect this gravitational field of the superposition state. Maybe there's a bit more intricate way, a better way to sense this gravitational field. What about, for example, interferometric sensing? This was discussed by Friedrich and others, who conclude that you get the same constraint, and then in that case where Bob does an interferometric experiment, a Cow experiment, to sense a phase shift due to this gravitational field. This critical constraint comes from the fact that when you look at your interference fringes, you need to require that interference fringes are at least a Planck length apart, and that will give you the same limits. So this was the experiment that has been presented, and now I add a fourth proposition, and that is actually the part where I want to look at the differences between electromagnetism and gravity. And so it has been suggested to look at effects that you get if you basically introduce post-Newtonian effects, post-Newtonian corrections into the Schrödinger equation with a heuristic motivation that can either come from time dilation effects or it can come from a mass defect interpretation where you say, well, the mass that actually enters the Hamiltonian, if I have a state that has an internal energy, is the sum of its rest mass and its internal energy. So both the gravitational field and the inertia coupled to this mass plus internal energy, and then one gets basically a coupling term of the internal Hamiltonian to the gravitational field, or to the gravitational potential. So this you can look at this purely classically, and there's a derivation for a classical model of an atom by Schwarz and Giulini. And so it's important to know, so in this derivation we actually get mathematically this expression. So it's important that you have to be careful with these heuristic motivations, right? So you can either understand it as time dilation effect or as mass defect. But if you would have done both, right? If you would have need to take into account both time dilation and mass defect, you would have basically double counted the effect. So that is one message that I want to send out. So be very cautious with heuristic pictures, what you're doing there. But then the idea is, so okay, now if we quantize this Hamiltonian, then we get a coupling term between internal and external degrees of freedom. And this has been used then to conjecture effects such as a time dilation decoherence effect by Koski and others in 2015. So those things I don't want to talk about here. I will only need the fact that the mass is in some sense dynamical of the system. I don't have to talk about superpositions of internal states. 5 minutes, okay, thank you. I only will talk about the possibility to have an internal state that we can excite to some energy level. I skipped this since I don't have that much time. So this is then the modified version of the thought experiment. So it's the same experiment. We do an interferometric detection of the gravitational potential of Alice's superposition, but what we can do is, so we have some Schengel experiment. We separate our particle in two trajectories depending on its spin, and then we use some, say, 2-photon absorption so that we don't disturb its momentum, to excite our state to some higher energy level. And then we let it propagate for some time tau, where it can interact with the gravitational potential. And then we use the stimulated emission to bring it back to the initial state before we accelerate it again with a magnetic field and and bring it back together. So you can look at this as an initial state that has the entangled state of the spin with the trajectory, with the position state. And then if you look at what the final state is, you will find that Alice's state is now entangled with the spin state. And you can choose the gravitational field in such a way that you end up with two orthogonal spin states, and you can basically measure with probability 1 which of the two configurations for Alice is the correct one. And this requires that the relation that is given here, that delta Q is of the order of the distance to the fourth divided by E times tau times D. So notice that here the internal energy, or rather the full energy, so E plus M if you want to be precise, enters in this gravitational effect, but on the other hand the fringe visibility effect, because we have the mass small m at that point, is still determined by the small mass. And if I put those two things together, then I find that the criterion for signaling can actually be satisfied if I assume that this internal energy is much larger than the mass m. So I have to hurry up, right? So there are two obvious objections to that. The first one would be that you need E much larger than m, which you should be careful with, because we know that most states we use in laboratories, atoms and so on, have mostly internal energy. So this is something we do regularly, that we have internal energy. So the only difference here is really that we can dynamically change this internal energy, not so much that the energy is internal energy rather than rest mass. And the second thing you could argue, well, do those photons send off rich path information? But I think if you just use a broad beam for the absorption and choose the trajectory slightly different, you can also avoid this problem in a consistent way. And so now I'm at a point where I wanted to conclude that this points to some issue with the four assumptions, but I think there is actually another resolution. And this is, you have to consider that when the absorption of photons happens, you emit gravitational waves. And if you look at this in detail, you find that this then gives you an inconsistent requirement that the distance over which you signal is smaller than the distance of your superposition. And so the conclusion I would not draw from this is that you can use this in sort of consistency condition that you need in order to propose gravitational decoherence effect that you could have come up with by yourself just without this thought experiment, but it points towards this, and it's quite interesting. So you can basically argue that when there is an absorption of photons, the localization of energy that happens with that must in some way emit gravitational waves. And this will lead to decoherence of the superpositions. That even if I have perfectly coherent photons basically in a flat space-time without any without any gravitational field. So sorry, I had to rush a bit at the end.
I think we have time for one very important question.
Yes.
Maybe here, yes. No. Okay.
Could you go back to the slide where you referred to a semi-classical gravity?
If you say stop, why not?
No, just about the fourth.
That's too far back. Here?
Yes, right. I think there are two levels of confusion, at least conceptually. First of all, let's look at the semi-classical gravity. I agree with that statement, but the important thing is that you have to include back reaction of the T mu nu in a self-consistent way to say that the sources need to be like that. in order to go to, you have to go to stochastic gravity, right? But then the first line there, what you said, seemed to suggest that gravity results in entanglement between source and test mass. In fact, when you look at that, it's actually at the test field level. First of all, there's no demand of self-consistency between the source, the mass, and the gravitational field. It's a test field, so you pick any gravitational field background. And more importantly, the two masses could be entangled through its quantum nature. And the gravitational field has nothing to do with graviton or says anything about the dynamical degree of freedom. And so that kind of experiment that you pointed out cannot say anything about the quantum nature of gravity, let alone perturbative quantum gravity, or even worse, quantum gravity at the Planck scale.
I agree to some degree with the second point. So I would object to it. So I agree with you that, just for what you said at the beginning, I agree with you that you need a consistent way to introduce back reaction. I wouldn't go that far as to say that leads you automatically to stochastic gravity. I would say it needs you need to introduce a way of wave function collapse, right? Your semi-classical gravity can only be consistent if you also have a consistent description of wave function collapse. So that is what I understand of semi-classical gravity. I know that we have slightly different ideas of.
That's right, but you have to make it very clear as you present it here. It's almost like the test field, you can see it, but semi-classical with back reaction, you cannot.
Yeah, we should discuss afterwards. That would have been an entirely different talk. I could talk about that. But yeah, I don't want to go into the details. We should discuss afterwards.
Okay, so I think we have to move on. Let's thank you.